Hello to everybody, my name is Goodwin with HV Diagnostics, and we're going to be talking a bit today about offline partial discharge testing of medium voltage cables in the field. We're not going to be talking about online. I will miss it every now and again, so there's some interest in that as well. But we're going to be talking primarily of offline. To understand any form of testing on a cable, doesn't matter if it's purely high voltage testing, diagnostic testing, which could include tan delta or partial discharge, or a host of other diagnostic techniques, you need to understand the construction of a cable. And if you look at the construction, there needs to be a clear understanding of what the different components are and what are their purpose. So obviously the first part is the conductor, which conducts the current down to the load. But that is covered by a semiconductor shield. And that semiconductor shield is there primarily to take any sharp points away from the conductor and have a very smooth interface to the insulation. The insulation could be anything from on the left, XLPE, to on the right, an EPR type construction. In general, EPR is used mainly in industrial, can be used in distribution as well, and XLPE tends to be, in general, more popular on the distribution side. That is covered by an outside insulation shield, which again forms the purpose of creating a very smooth interface between the between the copper concentric neutral cables, as you can see on the left, or the tape shield copper that you can see on the right. So any sharp points that may be on those two metallic elements don't become sharp points that get directly attached to the insulation. That could cause potential discharge and breakdown of the insulation. In both cases, on these pictures, you can see a jacket. Not all cables out there are jacketed. There's quite a lot of unjacketed cables too, again, particularly in the distribution area. Partial discharge testing on a cable can only really be done down the cable. In other words, you can look down a cable if you have a shielded cable. So if you don't have a concentric neutral or a tape shield type construction, it is extremely difficult, if not impossible, to look down the cable. And that's a very important part of understanding the cable and trying to apply partial discharge. You need to make sure there's a shielded cable. If we look at the IEEE 400, it has divided medium voltage shielded cables into two main groups for our purposes of field testing. The first group is extruded cables. I would imagine most people on the conference call would really be testing those types of cables. They are grouped, the grouping includes XLPE, which is cross-linked polyethylene, the EPR compounds, and they're varied compounds from different manufacturers, butyl rubber, which is an older compound that is no longer used but can be found in the field. And another predecessor to the XLPE is high molecular weight polyethylene. That's another type of material that is all grouped together and extruded. And most people will be testing extruded cables. In a lot of the old cities, you have laminated cables, such as paper lead or oil insulated cables, and they form a different group. And there's a good reason why these cables have been grouped into these two main categories. The IEEE also defines three types of field testing. So that doesn't matter if you're doing a withstand test or a diagnostic test. They can either fall under installation test, which is done on a cable reel, for example, or before the installation of any accessories onto the cable, and obviously well before energization of the cable, followed by a commissioning test, which is done on the cable but before energization under the power frequency or under the grid. And finally, this is the one that a lot of us get involved in as well, is in the maintenance testing, trying to assess the condition of the cable during the life of that cable. As far as withstand testing of cables is concerned, you either can do a withstand test on a cable where you don't monitor too many things, it's really just a pass-fail type test, or you can monitor a condition. Doesn't matter, partial discharge, tan delta, any form of diagnostic parameter that you monitor during the withstand test, which is a smart withstand or a monitored type 2 type test. I'm not too sure where the terminology type 1 and type 2 came from. It's a bit odd, but in any case, that's what's in the 400 document, IEEE 400 document. So we look at the simple withstand test, and you may be asking why we're talking about withstand in a partial discharge discussion. Well, when you do a test on a cable, and you do a partial discharge test, you need an energization source. So you need to apply voltage whether you like it or not. So you can't go into a project and say, I'm going to do a partial discharge test but not energize the cable. You have to have an energization source. So if we equate that to hydraulics or a water pump situation, we're feeding from a water pump into a pipe that's been flanged off, in other words, an open-circuited cable. And for those who know the analogy, the pressure in the pipe is analogous to the voltage, and the flow is analogous to the current. And effectively, when we do a simple wristband test, there are two outcomes. It either passes or the cable fails. If it fails, you get dielectric failure, you have to find the fault. And it pretty much tells you very clearly if you have a problem in the cable or not. There's not a whole lot of diagnostic value to it, but make no mistake, if the cable fails, that cable shouldn't have been in service in the first place, particularly under the voltages prescribed by the IEEE. IEEE requirements for offline testing. It is not recommended to use DC on extruded cables. I should really have extruded there. There is a standard for testing with DC on laminated cables like paper lead. But again, a large part of what we test is not paper lead. AC is only recommended test voltage to use, and that applies to partial discharge. Even if we could use DC on the cables, we wouldn't be using DC to do a partial discharge test on the cables in any case. AC testing, therefore, let's look at that in a bit more detail. We can obviously use power frequency. Power frequency AC test sets are available. There are some limitations we'll talk about. You can use low frequency VOS. I'm sure a lot of you heard about that now. And there are other things like oscillating waves that really try and combine a combination of the power saving ability of VOS and the power frequency aspects of testing at power frequency. So there are other types of techniques, but the primary ones are power frequency and low frequency. The problem with the power frequency is obviously energizing the cable. It is not easy to take a 110 volt power supply out of a wall or a small generator and energize the cable. The cable is electrically a large capacitor, and the longer that cable becomes, the more capacity you have in parallel, and clearly the bigger the capacitor this will become. And so the power required to energize that cable is given by that formula over there. Clearly you can see by the formula, power is very much dependent on frequency, the capacitance, and the voltage. Now the applied voltage, you can't really do anything about it, you have to follow the standard. The capacitance, you can start cutting the cable up in half or quarters, what's called the salami method, and that's not very popular with a lot of customers. Or the other alternative is the frequency to bring that down to try and minimize your power requirements. Now why is this important? Well, as an example, if you take a 1,000 foot run of 15 kV cable and you test it at 16 kV, which happens to be the IEEE test voltage for 15 kV cable maintenance, you will require a 10 kilowatt power supply at 60 hertz. And even if you use resonant techniques, it's still going to be a substantial amount of power that you need. If you make that cable longer, or you test it at higher voltages, the power requirement becomes even more severe, causing severe limitations, not only on the practical aspects of testing, but also on your things like the length of cable you're able to test. If you do it at 0.1 hertz, it's based on that formula, you can see you need 600 times the energy. At 0.1 hertz, you can energize with a 20 VA power supply. You can almost get that out of your battery through a simple inverter connected to your car battery. So 60 hertz versus VLS, obviously VLS is much smaller because of the power requirements are smaller, lighter, cheaper. 60 hertz is larger, more expensive. Both are AC, however, and both should be a sine wave. They should not be any other type of waveform. The DC high pod has obviously been replaced by an AC high pod, not only for the purposes of with that testing the cable, but it's for the purposes of partial discharge or offline testing as well. The VLS waveform is 10 seconds long. You can see by that waveform over there. Because we have a capacitive load, you can see you have a current voltage phase relationship of about 90 degrees. And you can get various parameters as well from the VLS, such as current, capacitance, etc. There are different types of waveforms out there. You get a pure sine wave like you can see on the top. The bottom left-hand side is called the cosine rectangular waveform, which is acceptable from a wristband point of view, but we're very difficult to do any form of partial discharge testing with it. important that you try and get a good, clean sine wave when you're doing partial discharge in the field. It may not be important if you're doing a purely a withstand test to have a perfectly good sine wave, but it certainly becomes important from a noise point of view if you're doing noise testing, or even if you want to do accurate tan delta testing. If you look at the IEEE table, this is important because if you're going to be performing a partial discharge test offline, these will become your maximum voltages. So I'm not going to go through each voltage here, but you can see this is up from IEEE 1.2, I should say, for 15 kV cable, for example, common cable. If you're doing acceptance testing, you go up to 20 kV. If you're doing maintenance testing, you go up to 16 kV. That means when you're testing a cable and you want to make sure is it partial discharge free, you want to make sure that it's partial discharge free up to 16 kV if it's an existing cable, or up to 20 kV if it's a new cable, and we're talking about a 15 kV rated cable in the same situation. And the same would apply if you're dealing with 25 kV or 35 kV cable. The Cellular standards for the international European type community, they use 3 times operating voltage, RMS phase to ground operating voltage, and their duration is 60 minutes. We have a slightly different standard for IEEE. Alright, the question of withstand testing, a possible outcome. Remember that a water pipe, either the water pipe holds the pressure or it doesn't. Well, the bottom left-hand picture here, you have a lineman down in a manhole with that T-body blew up under power frequency while he was down there. And even though he fortunately wasn't hurt, you can never be guaranteed of that outcome. It's not even a mile away that other T-body on the right was tested with an 80 withstand test and it failed. And you can't even see the damage to the elbow. You actually have to open it up before you see the damage, because you limit your current dramatically when you're doing offline type tests versus an online type of environment where anything does flow. You can have whatever the fault comes is dramatically cause not only collateral damage to equipment but also potentially to people as well. So 2 boxes there just highlighting what I've just gone over. Okay, so if we now look at the monitored type of test where we monitor a particular type of diagnostics, again we have the same water pump feeding into a pipe which is equivalent to our cable, and while we do this we actually now hook up a form of diagnostic onto the cable. What we're talking about there is partial discharge during application of voltage or pressure in this case. So from a healthcare perspective, that's what I'm looking at now. Instead of just jumping on the treadmill and making sure you don't have a heart attack, what you do, you now hook up an EKG onto the patient. The EKG is not that useful if the treadmill doesn't work. And so the treadmill needs to turn so you get the heart rate up. Same applies with the cable, you need to get the voltage up so that you can look for potential problems in the cable. So, just in summary, the high-pass test that we are still going to be using a AC tester, make no mistake, but if you just treat it as a pure high-pass test, it's a pass-fail type test where you're looking at diagnostics, we're getting a better understanding as to the condition of the cable. And that's quite useful. You can start to do proactive cable replacement, or sections of the cable can be replaced based on what you see with the diagnostic. If we look at the IEEE standard, and I would encourage some of you to go and have a look at the standards if you haven't, there's an IEEE 400. There's a brand new 400 standard that came out, well, not new standard, but it's a new revision of the standard. Came out in June this year, and that's got a lot of very, very good information in it. It's a real improvement on the original 400 document. There's some really good guidelines as to what methods it should be used when in that document. And then the sub-documents under 400, which is kind of the parent document, is the 400.1, which is for DC testing of paper-lead cable only, not for extruded cable. The 400.2, which is a VLF standard, which includes things like tan delta VLF, partial discharge at VLF. And then the 400.3 document, which is primarily just for PD, includes things like VLF, includes things like power frequency. And so there's a bit of a crossover between 400.3 and 400.2 when it comes to VLF PD. There's a combination of both of those installation of the smart test on the cable. So we're going to be hooking up an additional diagnostic measurement interface while we apply the voltage. The two most common methods are without doubt, hand delta or dissipation factor, and I refer you to IEEE 400.2 on that, and the other one is partial discharge. And both of those methods can be applied. Typically, hand delta you apply it at half operating voltage and you step it up to the IEEE test voltages, as I showed you in that previous table. With partial discharge, you typically start at operating voltage and you end up at the IEEE test levels in that table as I mentioned to you earlier. So let's look at partial discharge testing of shielded cables. We know now what type of power supply we need for it. Let's look at the actual diagnostic interface. So partial discharge, definition of it is a local electrical breakdown that only partially bridges the insulation. So you can get partial discharge in anything from generators, motors, switchgear, transformers, etc. We're dealing with cables now, but the same applies here. So a partial breakdown of the insulation of the cable. And it's important to know that partial discharge doesn't by itself collapse the voltage of the cable. So we don't have a dielectric failure. So if you pick up PD in a cable, don't expect to go and hook your thumb up onto the cable and find the fault. It's not going to be there. Don't expect that your relay protection is going to see the fault either. It's not going to be there. PD is a very, very small signal that is generated inside the cable. There are singular events. So you don't just look at one event, you look at them statistically. So what you'll be looking for, if you have a discharge in a splice, you'll be looking for a number of discharge patterns coming from that splice. And this may be obvious, but to a lot of people it's not that obvious. Only partial discharge generating spikes in the cable can be detected. If, for example, you have a water tree, and you could have several 100,000 water trees in the cable, they don't generate PD. So you won't be able to find water trees using PD. Either if you have a void in the cable, or a defective termination, for example, where they're cutting too deep into the insulation, you could find it with obviously, quite not all defects in a cable generate PD, for example, water treatment I mentioned. Okay, so characteristics of a PD. And as you can see, I've listed a whole series of different characteristics that can determine the size of the PD or the intensity of the PD. So first on the size of the defect, typically if you have a bigger void, for example, if you use a void as a source of the PD location, the bigger the size, the higher the location of the PD spike. In other words, where inside the cable is located, closer to the outside shield, closer to the conductor. Types of materials, there are even materials that are so-called PD resistant. So obviously if you have a cable that's PD resistant, PD may or may not even occur, and if it does occur, it may not be detrimental to the cable. Mechanical semiconductor shields, clearly be measuring the PD characteristic, and we have different types of semiconductor shields. They will influence what that PD impulse looks like. The applied voltage, if you bring the voltage up, you may not see any PD at operating voltage. You bring it up higher, you start to see PD stuff. Temperature, clearly the temperature changes can affect the characteristics of the PD as well. Time, attenuation, and others. So I've given a whole list there. Attenuation maybe requires a bit more explanation. Whenever you have a high frequency pulse taking place inside a cable or any apparatus for that matter, as you travel further and further away from the source of the PD, you get attenuation of that impulse taking place. So you are limited by the length of cable and the construction of the cable as far as the PD is concerned. So if we look at the units of PD, typically they are either in millivolts or in picocoulombs or nanocoulombs. Coulomb is the measurement. And as you can see over here, we have the PD impulse, and I don't know if you can see the mouse here, but the incident impulse over here, that has a PD amplitude of 540 picocoulombs, and the millivolt millivolt signal, you can get an idea of how small PD impulses are compared to the applied voltage. Very, very minute discharges that take place. So it's quite remarkable that you can actually detect something like this in the field, which has really only come about in the last 10, 15 years. Sources of PD in solid dielectric cables like XLPE, I've listed a few here. Void interfaces, if you have a gap between interfaces, so between a joint body and a cable. Electrical trees, defective accessories, an energized electrode and a floating conductor. That last point is highlighted here where you've got a concentric neutral that's corroded on the outside of the cable. And because you've got that corrosion taking place, you don't get good contact of the ground wires to the outer semiconductor, so you start to get arcing take place. And that arcing can split holes into the outside semiconductor and finally break down the cable. PD can also occur in paper lead cables, so you can see over there, in the paper lead cable that's got PD activity that's been present. Both on the left-hand side, and if you look at a paper wafer, you can see on the right-hand side a small, it's like a tree that's taken place due to partial discharge activity inside the paper cable. One thing about paper cable, it does have a tremendous ability to actually quench or self-heal itself when it comes to PD, which doesn't tend to be a property of cables like, for example, XLPE. So if we look at partial discharge exception voltage, as I mentioned earlier, you have to bring up the voltage, and at some point you will find that PD will take place. That's called the exception voltage. And if you look at this diagram on the right over here, what happens if you take a classical void installation, you get constant field lines, but because of the difference in permittivity, basically the property of the air versus that of the outside insulation, you get a concentration of electric fields inside that void. And as that electric field strength gets higher than what the air can actually take, you get a breakdown that takes place. And so we look at the next slide, you can actually see that breakdown that's taking place, which actually neutralizes that tension inside the void for a short time. And so when that occurs, that transient that takes place is the measurement that we're looking at, is measuring that transient change in electric field distribution as the partial discharge takes place in the cable. Go back to the previous slide, the extinction voltage, which is the PDEV, that's the voltage, the applied voltage at which PD ceases. In other words, PD no longer takes place. And the inception voltage of PD is not equal to the PDEV. In other words, it tends to extinguish below the voltage in which it incepts. So if you, let's say, it incepts at about 20 kV on a cable, you may find extinction is about 16 kV, for example. Alright, so let's look at the partial discharge waveform and how it's generated. So what we have over here, we have a cable. This is the near end where we hooked up the PD detector. We have the far end over here. We have the source of the PD in the cable over here. So this is the length of the cable from A to B. We're measuring at point A with our detector, and so let's see what happens if we get PD in the cable. So PD discharge occurs. The transient travels out in two directions. One hits the far end over here. The other one comes in towards us and hits our equipment, which triggers the equipment just like a normal oscilloscope, and that's what we see. And then, after a short while, that wave, which is the original reflected pulse of the far end, comes in as well. And the distance, basically, between this cursor over here and that second waveform over here, as you can see at the major, is the distance between the far end and the source of your PD. So I'll just go through that one more time just for folks to have a look at it. By the way, when you look at this thing, we do slow it down just to try and highlight different events that take place. But in reality, this is one continuous movement at a constant velocity. That velocity is the velocity of propagation of the cable, which is typically around about 500 feet per microsecond. It changes slightly from one cable to another, but it doesn't slow down the way it's shown here. Alright, so if you look at that, you get a fair idea of how PD transient takes place. You can see PD wire, if you have a long cable, is it has to travel quite a substantial way down the cable, so you do get attenuation. You can see this guy here is attenuated quite a bit because that's, if you remember, the PD pulse that went there, it's a third of the way, and then it's full into the cable, so it travels 1 1/3 of the distance, where this guy you travel 2/3 of the distance. That's obviously bigger, sharper, where this guy is lower and fatter. Alright, so the bottom line is this distance from here to here is the distance from the cable end. You can take the cable end and, minus your distance from the far end, and that's where you will walk out from and find your PD site. This distance over here, not that important, but from here to here is really this distance from there to there, which is double the cable length. Alright, if we do a PD test sequence, this is typically how we train people how to do it. We start off with operating voltage and we step up the voltage in gradual steps. Looking for PD, if we see PD, we capture it. If we don't, we just keep moving on. And we end up at the IEEE test voltage. And this, if you want to do a combination, we combine it with a withstand test to make an intelligent withstand test. And we just need the PD monitoring during this whole process. So really, this is a PD measurement, and so is this, but this is also a withstand test on the cable. You'll see a bit later why that can be important as well. Alright, if we look at some actual traces from the field, you can see over here, this is a PD impulse, and this is the second impulse, and so the distance from here to here is 143 feet, and that 143 feet is from the far end. This is a 25 kV cable, and so we'll measure a number of these triggers, and we'll build up what we call a mapping diagram over here. We can see each of these X's represents a PD site, or a PD trigger from the same site in the cable. So that's why I mentioned, don't look at the singular events, get a number of hits at the same location. And this was in a splice, 143 foot from the end. And interestingly, on this cable, the cable actually failed during the withstand portion of the test. I think I do have a picture. The cable actually failed at the start. So PD location consists of the calibration that we do, and we have a small calibrator that you can do offline. Clearly online, when you're relying purely on operating voltage, there's no way to physically hook onto the cable. So calibration can become very difficult, if not possible at all. But we always calibrate each and every time we go out there with PD to make sure that we understand how big the signal is. We do PD amplitude detection. That's obviously how big is the PD, called the Coulomb value. And then clearly based on the two pulses, we can do location on the PD site as well. Setting up of the equipment, you have a power supply over here. You have this filter capacitor combination over here, which really captures the PD. This is our cable under test that we have over there. We do try and use corona protection to avoid discharges in the air, which is also partial discharge. So we don't want to be contaminated our data by having external discharge. We are interested in the cable, so we do need to go through some housekeeping, no different than you do with PAN data. And so any PD that takes place in the cable will travel up here, go into the coupling capacitor, then down into an amplifier, into a PD detector, which you can then analyze on your laptop. Throughout this whole process, you are manipulating or changing the voltage from your VLF unit, again, starting at operating voltage and bringing up the voltage to the IEEE test level. So hopefully that's understood. Example PD project, and this really, in conclusion, I want to show you and highlight to you a project that we're involved in that highlights the benefits of PD and also of withstand testing. So there was a wind farm constructed in 2008. There were 4 installation faults during service. So we did the testing, I think, in 2010. So within 2 years, they had 4 cable faults, which is obviously completely unacceptable to the customer. The failures were checked, and the defects were found to be manufacturing defects inside the cable. And obviously with that, the customer was very concerned, so they have asked us to do testing with the company to actually verify that the remaining cable cables in the ground were fit for service. All the cables in question were 500 MCM, and these are, at most wind farms, very long direct buried cables with very few points of access to the cable. 35 kV cable, 10,000 feet long is kind of an average range. Cable characteristics, 2007 cable was made, 35 kV rated, tree retarded copper polyethylene. This is very typical for most wind farms. 500 kV more copper, concentric neutral design, jacketed direct buried. And the good thing about the cable, every single site has GPS tags, so it's very nice to go and locate the flights and work. So the testing diagnostic approach, we would energize 10,000 feet of cable, which is obviously a very long length of cable. We couldn't go much longer than that due to power requirements and also access limitations. So we had no real access other than about 10,000. There were no junction boxes, for example. We had to monitor the PD coming from the cable or the accessories, and obviously if there was PD, we needed to analyze the waveform so we can actually detect whether it was inside the cable, which was more of a warranty issue, or inside the accessory, which fell on a different responsibility area. And any PD detected inside the cable was considered to be unacceptable. That was just the agreement we came up with the supply of the cable. Any PD that would be the end of the cable. So if you look at the typical situation of those of you who've done testing on wind farms are familiar with the typical T-body installation. And we look at now the calibration pulse that we inject artificially into the cables to calibrate our system. You can see over there a very nice reflection from the far end, and just bear in mind this is 10,000 feet of cable, which is a very long length of cable. So clearly we see attenuation of the impulse. So this big impulse has been reduced to that, but you can clearly see the end of the cable. That's a 550 coulomb pulse. Then we do the PD measurements, and as you can see over here, we see a PD signature coming back from 8,156 feet. That is from the far end, so it's actually pretty close to us. And you can see the impulse, the PD picocoulomb value of the PD, in this case, 200 coulomb, so relatively it's big enough to be damaging to the cable, but obviously less than what we injected during calibration. We have another one at 8,981 feet. You remember the previous one was 8,156 feet. So what we've got here is actually two PD sites in the same cable over here. So it's quite an interesting situation we found ourselves in. And this particular PD impulse is 437 picocoulombs amplitude. Okay. So when we do what we call a mapping diagram, you can see over here you've got the two locations of PD sites in the cable. And the one being the 8,148, and then you've got the other one over here that's going to curve on. As you can see very clearly on an otherwise completely clean cable, two distinctive PD sites in the cable. Alright, so let's look at the observation. This 10,000 foot was 500 MCM. And interestingly enough, this was one of the cables that had one of those four faults that had occurred during operation in the 2-3 years of the wind farm being in operation. Location of the replaced devices could not be pinpointed. This cable had obviously been repaired before, so we tried to locate the devices. They were not GPS tagged. They were done after original construction. We couldn't locate them with the GDR. But from all accounts, it was nowhere near where the PD was detected. So clearly, the PD was inside the cable section. The amplitude of PD was seen as small as 240 picocoulombs and as large as 700 picocoulombs, to be a pebble measurement. And as a result of this, all three phases were replaced. They were not interested in trying to help the cable over the potential issue that they'd come up with before the testing. The additional test results are quite interesting. The PD sensitivity was great on a very long length of cable. But, obviously, if there's a defect in the cable and it doesn't generate PD, as I mentioned earlier, PD won't detect it. So if you remember, we also are applying voltage throughout this whole process. We are going offline and elevating the voltage. So that's an important part of it, because not only is PD giving you some information, but the wristband itself, not just the pass-fail, it tells you if the dielectric integrity of the cable is good. So PD was not detected in all cases. However, importantly, 3 splices failed for 1 hour wristband test. Publication methods were used, and these failures were found. As you can see a picture over here, the sharp edges of the barrel connector connecting the splice had completely cut through the strip material that they put around there, and it actually penetrated the splice volume. That's where it failed. And so what's interesting about this particular one, and the one I'm showing you here, some failed on the PD and some, as I mentioned, failed on the wristband. The wristband caught some of the defects, while the PD caught some others. So the combination of the wristband with the PD is a very, very good thing to do. And by the way, that's also what cable manufacturers have to do. They have to do a PD test and a wristband test on a cable. Right, that brings me to the end of the presentation. I think I went a bit longer than anticipated. So I don't know if you have any questions, I can maybe answer a few of them. I guess Aaron, you're going to take over.
Yes, we had a question. I think it referred to the beginning of the presentation, and it was, what is the difference between the output styles in VLF, trapezoid versus sine wave, and is there any impact as it relates to the partial discharge testing?
Well, with the square wave or cosine rectangular waveform, it is, I've seen one paper written where they did some testing, but it's really not used in the field at all that I'm aware of. And the reason being is that it's quite a noisy waveform. There's some very sharp transitions that take place. And so, as far as I know, in North America, I'm not aware of any PD tests that have taken place with that waveform. Typically, the waveform applied with any partial discharge test is done at, it is a sine wave. The frequency may vary, but the sine wave is used. And you want to try to keep that sine wave as smooth as possible, limit the harmonics in the sine wave, make it load independent. These are all variables that are very important. If you don't have a clean supply, it becomes very difficult to get to stop your PD system from triggering or mis-triggering on a noisy source rather than PD coming from the cable itself.
Perfect, thank you. And then also, if you're attempting to measure partial discharge on a branched or network circuit that has T and Y connectors, does that present any different challenges or differences?
Yeah, that presents a very big challenge. And the challenge is for anyone who's used a TDR before, I'm sure you'll know, you get multiple reflections coming off each branch of that network cable. So I know there are some techniques that have been looked at where they look at utilizing GPS tagging or some form of time synchronization to try and pick out where the PD sites are coming from. But the ones that I have seen are extremely expensive and relatively cumbersome to set up. However, the bottom line is if you do have a network type environment, you have an incredibly difficult challenge to try and figure out the location of the PD. You just use the TDR tracing device. So it does pose a significant issue. The other issue that you've normally got with that type of a micro network cable is that you normally have multiple different types of insulation as well on the cable. So a lot of our customers that we talk to you about, they tend to just use on those types of cables either a tan delta, which tends to be independent of the fact that there's a network type cable or simple wristband testing on the cable. Partial discharge becomes very challenging. The same applies, by the way, with fault location. Fault location techniques that use TDRs become very, very bogged down with the network type cable.
Fantastic. And also, how does cross-bonding affect the measurements?
Cross-bonding on partial discharge, what you have to do at the cross-bonded section, you have to do a straight through connection. So depending on the construction, normally they bring the tail down to a common junction box with an normal refrigerant in that junction box. You need to have a straight through connection at the cross bonding station. And if you don't do that, you can obviously be affected by the fact that you've got the concentric neutral of one cable now moving into the next phase, which unfortunately makes it very difficult to analyze the information. So at least for a temporary situation while you go offline, take A and take it all the way through to A and B all the way through to B. I'm talking about B up to the concentric neutral, and don't zigzag it across as you normally do in the cross-bonding situation. Cross-bonding is useful for increasing the rating of a cable, but we're not talking about carrying any load when we're doing testing. So for testing purposes, always try and use a straight-through connection. As far as BLS is concerned, there's no, if you're doing a BLS test, cross-bonding has no impact on it. As far as tan delta is concerned, it has no impact on it. The partial discharge is just like any TDR technique, you have to have a straight-through connection.
Perfect. And actually, questions are coming in now. More questions. So, do you have any experience with cables that have been silicone injected? Does that add challenges?
I have injected some, typically normally by accident. As far as partial discharge is concerned, the idea with silicone injection is to convert water trees into insulation. And the measurements I've done have been more tan delta measurements rather than partial discharge. But I've never seen partial discharge in a cable that's been injected to date. Whether or not they have it, people in the field, I don't know. But I've not heard of any discharge activity in a cable that's been injected. Remember, in an XLP cable, if you tend to get electrical tree take place in the cable, which is really discharge activity in the cable itself, it normally is very, very rapid for that cable to go to failure. It's a very devastating impact. So while you can measure partial discharge in the cable, it normally takes a very short duration for that cable to fail. So most of the time when you go out and do PD testing on the cable, you don't generally see PD coming from the cable, particularly if you're operating voltage, because if it was there, it normally would have failed before you got there. Where you normally see PD, particularly operating voltage, is where you've got accessories which can tolerate PD for some time before it fails.
Perfect. And does it matter what you calibrate the test at? For example, if you calibrate at 5 nanocoulombs, will that hide partial discharge levels below that?
My recommendation is to try calibrate at the lowest possible value that you can. With some important points being, you need to make sure you get a reflection from the far end of the cable, and you need to make sure that the PD impulse, the calibration pulse, is bigger than your noise band. You can meet those two criteria, keep the PD calibration pulse as low as you can.
Great. And would you mind for a moment just discussing the difference between VLF AC and damped AC?
The damped AC, typically, they try and get the frequency close to the operating frequency. It can vary anywhere from 20 Hz to 400 Hz. The actual final frequency rate depends on the depth of the cable, the capacitance of the cable, essentially. VLF obviously occurs at 0.1 Hz. So the real difference between the two, from a frequency point of view, is that the one is anywhere from 20, 30 Hz up to several hundred Hz, compared to the one being a very stable 0.1 Hz. The other thing about oscillating waves is that the VLF, the sine wave, continues load independency symmetrically one cycle after the other. With a oscillating wave, you pretty much have one full cycle. For the first cycle, and it began at 60 Hz within a few milliseconds, and that waveform then decays quite rapidly down to 0, and then you have to recharge up your oscillating wave system, and then reactivate the oscillating wave again. So you're only getting a very short duration, one one or two cycles where you're getting the full applied voltage on the cable. And in that 1 or 2 cycles, you're able to do peak version of 0.1 hertz. That cycle remains constant on the cable. There's no decay of the voltage with time as it is with an oscillating rate system.
Fantastic. Thank you. That wraps up all of the questions that have been submitted throughout the presentation. So I think that we are right on time. Greg, I'd like to just take a moment to thank you for taking your time to really contribute to the community with the experience and the perspective. Everyone that's on the call, thank you for your attention, your attendance. We're really trying to make an effort to make these a series of things that contributes to the education of the community. So if there's anything that you would like to see or that you would suggest to make these better or more valuable, please let us know. We'll be sending out emails with links to the video from this webinar as well as the schedule for the webinar next month. So please be on the lookout for that. And if you have any questions or if there's anything we can ever do, please let us know. Otherwise, thank you all for your time and have a great rest of the day.